here shows the percentage of period elongation. And this has to do then with the time step increment compared to the actual period of the spring mass. So as you go to smaller and smaller time steps, you get more and more sample points over the period of the oscillating mass. And of course, as your time steps become very, very small, the error becomes vanishingly small too. If you were to take a certain number of time steps, say 10 per period, then you would come up here and see that the Newmark method gives about 3% error, the Wilson theta about 5, and the Hubolt method about 8. And you can see in this simple problem that the Newmark Beta method would be declared the winner. Remember, though, that these other methods have been developed a little bit more for random force situations rather than a simple oscillator like this. When it comes to amplitude decay, and that's something in the nature of an artificial damping, the Newmark Beta method comes in with 0 error for all stepping sizes, whereas you do get some error with both the Wilson and the Hubolt methods, namely for 10 samples per cycle you get 7 and 12%. So it looks as if the Newmark Beta for this kind of work is probably optimum. Let's do a numerical example to exercise our knowledge of the Newmark integration. I've chosen a 2 degree of freedom spring mass damper system. I've picked unit masses here, as you'll see in the data that are given later. I've sized the springs and the dampers to make this be an interesting problem where there's some oscillation under this suddenly applied load shown below. I'm going to take the load on the right mass to be 100 units outboard positive. The other mass will be loaded with 100 units of load negative inboard. When the system comes to rest after some oscillations due to the dampers taking the energy out, you'll find that these two masses have moved apart and the live loads are equilibrated through a force in the spring K2, but the two live loads cancel each other and there's no net force through the spring K1. So you'll see this first mass on the left come to rest after some time exactly at its starting position, whereas the second mass will move outboard. Our goal will be to find the displacements for these two masses by using the Newmark Beta method. Now the procedure is to solve the Newmark equation using the values gamma of 5/10 and beta of 0.25. I've done this through a small Fortran program and have used subroutines that let me do the decomposition and solve steps that I had developed earlier for a static problem. The main program will set the physical constants, and then the numerical integration is done in the Newmark, or call it the Newmar subroutine. The live loads are given through this force subroutine. So using conventional Fortran programming, you use the artifice of a main program calling on subroutines and then dividing the tasks among those subroutines. I'll show the code in the following figures. The main program of the Fortran code is shown in this figure. Here I set up the dimensions and give the physical constants that I had to adjust until I got the system to be nicely behaving. My time step was 1/10 of a unit. Let's suppose this is in a Newton millimeter second system, and then mass has to be megagram. And then that would be a megagram for each of those masses. Pretty big, metric ton. We're really moving some heavy things. If you prefer to think in English, you can think of foot-pound-second system, and then the mass would be a slug, which would be a little more like, 2 bowling balls. That's more reasonable. Anyway, I set the beta and the gamma values here, and then call for the program Newmark to do the actual integration. The subroutine Newmark introduces the constants used in the Newmark Beta method and does the actual integration. One of the things that's calculated here is the k with the little caret over it. I've called it k hat here. The Newmark program's continued on this figure, and at some point calls for the force, which is calculated in another subroutine. The k hat, which is the matrix of stiffness coefficients, which really involve all of the inertia and the damping and the stiffness forces. K hat has to be decomposed into a triangular factorized matrix, and that's done in the decomp program here. I originally did this for a full matrix for static solution, and it can be used also in small problems for dynamics as we're doing here. The decomposition is a major step in this whole process, and by far the most expensive in computational terms. Then once you have that, you solve the problem, and this is all a part of a Gauss elimination set up in matrix form. And the solution then is you have a forward solution and a back substitution, and that's done in this subroutine solve. It's amazing how few Fortran commands it takes to solve even a large set of equations. This subroutine is not developed for a banded set of matrices, and so it's not good for more than probably several hundred equations. I enjoyed programming that small Fortran program, and it helped me run through the Newmark integration so that I got familiar with the various coefficients. I think that for some people it might be worth their while to go through that whole process. I don't really ask people to do much programming anymore in my finite element classes. One thing I do is the Gauss elimination solver in static problems. And this one here on the Newmark integration is the only thing I show people in the dynamic area. But for someone that's a real gunner, you might want to do your own programming. To do the banded version of Gauss elimination on that triangular factorization is a little more work, unfortunately, and that's going to be several days of work, and so I wouldn't do that lightly. And commercial solvers are so much better by now anyway than anything we can hand program that I don't advise that. All right, here are the results coming out of this program FEMNU. And I plotted separately the displacement on the left mass and the displacement on the right mass. And indeed, the two forces tended to first throw the two masses apart by sending the inner mass toward the wall, but only roughly 1.5 units. And here on the outer mass, it was thrown outward quite a bit, as much as 10 inches, and then came to rest at a 10-inch displacement. I guess that might make sense if you look at the stiffness and the force involved. It sure looks like 100 units of force pushing against a spring with 10 units of resistance. And everything comes to rest then with the 0 deflection on U1 and this 10-unit deflection on U2. Now we'll have a problem session and have several problems using the Newmark method. Let's start with a spring mass system where it's hanging from the ceiling, but neglect gravity. We're going to assume there's a mass there, a point mass with this mass, and put a force on it. And we're going to say that it has these conditions at time 1.5 seconds. So you've been given both the displacement and the velocity. And then the question is, what would be the position at the next time step of 1.51 seconds? So it would be a hundredth of a second time step carrying it forward. Now, it is interesting to think then whether it's primarily the mass or the stiffness that will govern that motion. And if the time step is small enough, we know that the inertia terms are pretty big. We'll pick the standard Newmark values of gamma equals 1/2 and beta equals 1/4. The integration formula, when there's no damping, which is our case, is like this. And we have all required quantities except for acceleration at the starting time of 1.5 seconds. And that's needed, let's see, at this point here. That can be found from the equation of motion, and substituting in the numbers we get that. So I've just used the equation of motion itself to fill in one missing piece and see that there's quite a large acceleration here. A second important calculation is that for the k hat, and that's quickly found as 50 newtons per millimeter. So this is the effective stiffness. Then we go back to the integration formula, putting that number in where it belongs, and adding other things such as that acceleration where it belonged, and you pick up the current position of the body at 8.57 millimeters. Now, it was starting out in our first calculation at 1.5 millimeters. So it has moved a distance of roughly 7 millimeters in a hundredth of a second. Now I'd like to pose one of the simplest structural dynamic problems that you could pose to be solved with Newmark Beta method. Here's a beam that's clamped at the left end and guided at the right. That means there is no slope at the right end nor any shear force. So it's a roller skate condition. There's a 10,000 Newton vertical load applied there at time 0. We're going to study this system and find the response using one element and Newmark Beta method with 100-second time steps. There's no damping in the system, and you're given the results at a time 1.05 seconds, and we're going to be asked what is the solution at 1.06 second, a hundredth of a second later. Next, I give the material properties and the geometric properties. And here's a statement requesting the displacement at the tip at 1.06 seconds. This problem's a lot like the last one, and these appear as exam questions typically in my course, and so that's why they've appeared here in the problem session. So you can pretend you're under the pressure of a time deadline to do this in 20 minutes. Setting up the structural dynamic problem is kind of fun. You take one beam element, one Euler-Bernoulli beam element, since this is a slender beam, and then constrain the accelerations here at the root, and then the rotational degree of freedom at the right end. And after crossing out rows and columns, you end up with a scalar equation with only one unknown. We then go into the Newmark equation to be solved, and here it is for the single variable u3 at t plus delta t. Then I do some calculations for the structural mass and stiffness coefficients, and then we have to find the Newmark Beta quantities, the A's shown here and on the start of the next figure. After finding these remaining coefficients, we can solve the problem, and we take one further time step, bringing us to 1.06 seconds. Putting in all those terms, we find that the displacement is 2.93 millimeters. Now, it had started out at 2.73 earlier, and so it's moved 0.2 of a millimeter in 1/100th of a second. So I guess you could even calculate a velocity just by that simple differencing, or you can go in and really use the formula that you're supposed to use. Our final problem is to set up sort of an academic situation where we want to exactly integrate a process that has an acceleration field defined by a constant and a quadratic acceleration. It's vaguely possible to have such situations where you have perhaps a quadratic spring, say, or some force field which would tend to give you such an acceleration field. But it's a little bit far-fetched because this would be a special purpose Newmark Beta integration. So the idea is that we want to find the conditions that gamma and beta hopefully would have to give zero error in the velocity and displacement interpolation. And is it possible to develop such a special Newmark Beta method? So the idea is to look to the defining equations and see what we get. Well, we've already proven that the general Newmark scheme is identically satisfied for constant acceleration. We've been told that we don't need to worry about linear acceleration because it won't happen. So therefore we advance to quadratic acceleration terms and see if we can satisfy those when we're dealing first of all with the velocity interpolation. So this quadratic acceleration term t squared can be analytically integrated to give velocities and displacements. We look at the velocity interpolation formula, and that's the one that involves gamma. We put in this quadratic case up above, for instance, giving these acceleration terms t0 squared and t1 squared. And then we equate these various terms and see if it can be done. So we multiply out and simplify, and then we collect terms on the different coefficients here, and we find that we get contrary requirements here. So there's no way for arbitrary t0 and t1 to satisfy all of these. Now, I'm not completely happy with this solution because the only true variable here is t1 minus t0 over that range, and I would really rather cast this set of terms into only two terms that multiply t1 minus t0 perhaps to the first, second, and third power if it so happens. Now you might still get four of them, but certainly we see that it's not easy to figure a solution to this set of equations. I'm not certain if this is the only proper, I don't know that this is a necessary and sufficient set of equations is what I'm saying, but it was kind of fun just to look at this as first cut. If some real smart person in the audience wants to try this in a little different form, that would be great. I'm pretty sure though you're going to find that quadratic acceleration is going to be very difficult to satisfy, even adjusting both gamma and beta.